In this example, we have a heat pump with a given coefficient of performance, and we're told how much energy is going into maintaining a building at a certain temperature. This will be the hot reservoir for our heat pump cycle, and we're getting that energy from the outside, which is our cold reservoir, and that's given to be minus 5 degrees Celsius. We're also told the cost of electricity in terms of dollars per unit energy. A kilowatt hour is a unit of energy. We're asked to determine the actual daily operating cost and the minimum theoretical daily operation cost, and then we're also asked to compare the results of Part A with the daily cost of electrical resistance heating. So we're dealing with a heat pump cycle, and we're trying to find the operating cost. The operating cost is going to be how much energy we use multiplied by the cost of electricity. So the first part that we need to do is figure out how much energy this heat pump cycle is using. So let's go ahead and first get started with a drawing of the heat pump cycle. So here's our system. The system contains all of our components that operate the heat pump. For example, the compressor, the throttling valve, etc., those kinds of components. They're all contained within the system. We're going to put some power into this. We're drawing that. So the purpose of the heat pump is to pull energy out of the cold reservoir, which I'm drawing right now. So here's our cold reservoir. And we're given that the temperature of the cold reservoir is minus 5 degrees C. And we're pulling some energy out of that in our heat pump cycle at a particular rate. So we'll call that Q dot C. And then that energy goes ultimately into the hot reservoir, which is our building. So our hot reservoir. And that's given to be a temperature of 20 degrees C. So the hot reservoir is our building that we're trying to heat. And the cold reservoir is the outdoors. And the heat going from our system into our hot reservoir we'll call Q dot H. So the way a heat pump works is it moves energy around. So what we're doing is, even though it's cold outside, we can pull, or cold in the cold reservoir, it still has some internal energy to it. So what we're doing is we're actually pulling some of the energy out of that cold reservoir into our system. And the way we do that is the refrigerant in the system just has to be colder than the temperature of the outside. So that's easily done. We can have a refrigerant that's colder than that. So that gives us some heat transfer into that refrigerant. Then we do some work on the refrigerant, move it around, do some processing on it, and then we can release the energy that's in the refrigerant into our hot reservoir. That's the Q dot H. We just, again, to get the heat transfer, we just need to make sure that the refrigerant with our energy now has a higher temperature than the hot reservoir so that we get some heat transfer there. All right. Well, we're given the coefficient of performance for the heat pump. And if you recall, the coefficient of performance is related to the rate at which we're adding heat into the hot reservoir, because the goal of a heat pump cycle is to get energy into the hot reservoir. So it's going to be our rate of energy transfer into the hot reservoir divided by the amount of power that we have to put into the whole cycle. Because we want to get as much heat into the hot reservoir for as little power going into this heat pump cycle. So that's our definition for the coefficient of performance. So to solve for the power, what we would do is we'd just rearrange that equation. So we can solve for the power into, it's going to be Q dot H divided by the COP, coefficient of performance for the heat pump cycle. Well, we're given the values for these. We're given that the rate of heat transfer into the hot reservoir is 70,000 kilojoules per hour. And we're given the coefficient of performance as 3.5. So we can plug those numbers in and then solve for the rate at which we have to put work into our cycle. And that comes out to be a value of 20,000 kilojoules per hour. So that gives us the power that is required to operate the heat pump cycle. It doesn't give us the daily cost. So in order to find the daily cost, we need to multiply that power by the cost of electricity. So we'll do that. So this will be the daily operating cost. Will be our power, 20,000 kilojoules per hour, multiplied by the cost of electricity, which was 0.085, so 8.5 cents per kilowatt hour. Again, kilowatt hour is a unit of energy. We're going to convert this so that we get cost per day because we want the daily cost. So there's some unit conversions that we have to do. For example, 1 kilowatt is 1 kilojoule per second. We also know that one hour is 3,600 seconds. So you can see what I'm doing here is there's a second here, a second there, a kilowatt here, kilowatt there, an hour here, an hour there, a kilojoule, kilojoule. So now we have the cost in dollars per hour, but we really want this in terms of dollars per day. So we know that 24 hours, there are 24 hours in one day. So the hour cancels out with that. Now we should have dollars per day. And if you work out the numbers for this, this comes out to be $11.33 per day. So that's our daily cost. So what we've done is we've done the first part of Part A, the actual daily operating cost. Now the second part of Part A is to determine the minimum theoretical daily operation cost. So to do this, we want to find what our minimum amount of power is that we have to put into this coefficient of performance. So we want to have the highest coefficient of performance as possible, right? So if we want the minimum amount of power, we want the highest coefficient of performance. So the best coefficient of performance that we can have will be one corresponding to an internally reversible cycle. So the coefficient of performance, the heat pump coefficient of performance, the maximum, let me write it this way, heat pump, the coefficient of performance for a heat pump cycle, max, is going to be the coefficient of performance for a heat pump cycle for an internally reversible cycle, one that has no irreversibility to it. And if you recall from a previous set of notes, the internally reversible performance measures for a heat pump cycle, it depends on the absolute values of the hot and cold reservoirs. And if you go back to our previous notes, you'll find that that comes out to be the absolute value of the hot reservoir divided by the difference between the temperature of the hot reservoir and the cold reservoir. So we can substitute in the absolute temperatures for these. So in the hot reservoir, it's 20 degrees Celsius. But again, we'll convert this over to Kelvin. So we'll add in 273, and then we take the difference in the denominator. In the denominator, I don't really need to put in the 273 because I'm taking the difference, but I'll just put it here to be thorough. So there's Kelvin in the denominator as well. And when you work out the numbers for this, you'll find that the coefficient of performance maximum is 11.72. So you can see that the maximum coefficient of performance is quite a bit higher. So this 11.72 is quite a bit higher than our value of 3.5. So clearly we're far from the optimal situation. What it means is that potentially we could improve the performance of our components in our heat pump cycle. Perhaps we could do something to help improve the performance of it and make it a little more efficient. Okay, nevertheless, if we want to find the daily cost, the minimum daily cost, what we'd do is take this coefficient of performance, plug it back in up into the coefficient of performance up here. We'd still be moving the same amount of energy into the hot reservoir, so it's still 70,000 kilojoules per hour. But we'd put in our 11.72 here and calculate the new work. So let me go ahead and do that. So the new power into, and this will be the minimum power because we're using the maximum coefficient of performance. When you plug in the numbers for this, it comes out to be 5,973 kilojoules per hour. So quite a bit smaller than our, you recall that originally we had 20,000 kilojoules per hour, so now we're using much less energy. And then if we want to find the daily cost for this case, we'd go through the same procedure up here, but instead of the 20,000 kilojoules per hour, we would use the 5,973. So if we do that, so I'll call this the minimum daily cost. When you plug in the numbers for that, it comes out to be $3.38 per day. It's quite a bit cheaper than what we found previously, and that's because we're using the best or the highest coefficient of performance for our heat pump in this particular calculation. Now the last part of the question here, part B, is compare the results of part A with the daily cost of electrical resistance heating. So not using the heat pump, but just using a straight conversion from power into heat. So it's like using a toaster. So you put some electricity into the toaster coils, and then they heat up and release some heat energy. And that kind of process is 100% efficient. So what happens is the power that goes into the toaster is the same power that's going into the heat. It's 100% efficient. So let me just make a note of that. Electric resistance heating. So that's what we're solving for now. It's 100% efficient. If there were any inefficiencies, typically inefficiencies go into generating more heat. That's our objective here, is to generate heat. So as long as we're not putting energy in and it's creating sound or something like that, then it's 100% efficient. So whatever power we put into it will all go into heat. So in this particular case, we know the rate of heat transfer is 70,000 kilojoules per hour. So that's how much power we would have to put in as electricity. So you can see that number is actually quite a bit bigger than what we had previously for even the low coefficient of performance. Remember up here when we had a coefficient of performance of 3.5, our power was 20,000 kilojoules per hour. But now we're dealing with 70,000 kilojoules per hour, so our costs are going to be higher. And if you work out these daily costs using the same procedure that we did before, this comes out to be $39.67 per day. This will be for electric heating. So much more costly than using the heat pump. So you might want to ask yourself, why, if this electric resistance heating is 100% efficient, why does it cost so much more? Why does the heat pump seem to be a lot more efficient than 100% efficiency? And the reason is with a heat pump, we're not converting from electricity directly into heat. So we're not doing this direct conversion when we use a heat pump cycle. What happens for a heat pump cycle, go back up to the picture here, is we're moving energy around. The power that we put into it is used to move energy, not to convert energy. So we're not directly converting this power into heat. We're using this power to move energy around. So what we're doing is we're taking energy out of the cold reservoir. And remember, even something that's cold has internal energy to it. So we're just taking some of that internal energy out of this cold reservoir, and we're moving that energy up into the hot reservoir. And that's a lot more efficient than just the direct conversion. So that's why heat pumps are so popular, is because you can they're much less costly to operate. You're just moving energy around rather than doing direct conversions of it. And the way that we move that energy around, it all has to do with the system in here. We're taking our refrigerant in the system, and in this particular region, the refrigerant's very cold, and so we get heat transfer into it, and then we do some processing to it, and then when it gets to this region, it's hot, and we offload the energy into the hot reservoir. So that's why it's much more efficient to actually use a heat pump than an electrical resistance heater.